let us discuss ESR instrumentation and its applications. An electron spin resonance spectrometer, also known as an electron paramagnetic resonance spectrometer, utilizes a static magnetic field and microwaves to observe the behavior of unpaired electrons in a material, providing information about its chemical and physical properties. The core components are a magnet, a microwave source, a sample cavity, and a detector. With an ESR instrument, a static magnetic field and microwaves are used to observe the behavior of the unpaired electrons in the material being studied. The study of the behavior of the electrons in a sample gives information about the condition of the sample. An ESR spectrometer has 7 main parts. Klystron tube, which is nothing but microwave generator, attenuator, circulator, load, sample cavity, modulation coils, and diode detector with ammeter. So this is the pictorial representation of an instrumentation of ESR. So the first part is nothing but a source. Klystrons are commonly used as the microwave sources. It can tune the waves into precise frequency, amplitude, and phase. It will go through the attenuator, the second part, which is used to adjust the level of the microwave power. That is, it can homogenize the power of the incoming microwaves. And the microwaves are then channeled into the resonant cavity by using a waveguide, third part. It conveys the microwave power to the sample cavity. The resonant cavity is placed between the pole pieces of the electromagnet, fourth part. The sample is placed within the resonance cavity, which is a key component of the ESR spectrometer. The cavity is designed to efficiently interact with the microwaves and the sample. And then the signals will be obtained. The detector measures the absorption of microwaves by the sample. Usually, the crystal detectors are commonly used. So that is connected with the computer. We can have the signals at the computer screen. The first part is a klystron tube. It acts as a source of radiation. Microwave radiation is produced and amplified by a klystron tube, which is capable of tuning waves to precise frequency, amplitude, and phase. The microwaves are then channeled into a resonant cavity by using either a waveguide or a coaxial cable. Waveguide is the most commonly used. It is stabilized against temperature fluctuation by immersing in an oil bath or by forced air cooling. The frequency of the monochromatic radiation is determined by the voltage applied to the klystron. It is kept at a fixed frequency by an automatic control circuit, which provides a power output of about 300 milliwatts. So this is the klystron tube. The parts of the klystron tube, we have the heated element, which acts as the cathode. The electrons are coming out from the cathode, and there is an anode in which some holes will be there. These electrons will have very high velocity that will pass through the holes, and there is a reflector electron will be there, and it will come back and it will generate some oscillating electric field. So there are three parts: heating element, which is nothing but a cathode, anode, and negative reflector. The motion of charged electrons from hole in an anode to reflect and back to anode generates an oscillating electric field and the electromagnetic radiations. Attenuator. It is used to adjust the level of a microwave power. The power propagated down the waveguide may be continuously decreased by inserting a piece of resistive material into the waveguide. This piece is called a variable attenuator. It is used in varying the power of the sample from the full power of klystron to 1 attenuator by a force 100 or more. The attenuator homogenizes the power of the incoming microwaves. It does not change the frequency. It reduces noise. Waveguide or wave meter. The wave meter is put in between the oscillator and the attenuator. To know the frequency of microwaves produced by klystron oscillator, the wave meter is usually calibrated in frequency unit megahertz instead of wavelength. Waveguide is a hollow rectangular brass tube. It is used to convey the wave radiation to the sample and crystal. It is used to convey the microwave power to the sample cavity. Circulator. The isolator is used to direct the microwaves. It keeps the microwaves from reflecting back towards the source. Magnet system. The resonant cavity is placed between the pole pieces of an electromagnet. The field should be stable and uniform over the sample volume. The stability of field is achieved by energizing the magnet with a highly regulated power supply. The ESR spectrum is recorded by slowly varying the magnetic field through the resonance condense by sweeping the current supply to the magnet by the power supply. Electromagnets capable of producing a magnetic field of at least 5000 Gauss are required. The magnetic field must be stable and uniform across the sample volume. The ESR spectrum is recorded by slowly varying the magnetic field through the resonance condition achieved by sweeping the current supply to the magnet. Then the fifth part is sample cavity. The heart of the ESR spectrometer is a resonant cavity containing the sample. Rectangular TE120 cavity or cylindrical TE011 cavity are widely used. In most of the ESR spectrometers, dual sample cavities are generally used. This is done by simultaneous observation of the sample and the reference material. Since magnetic field interacts with the sample to cause spin resonance, the sample is placed in which the intensity of magnetic field is the greatest. It is constructed in such a way to maximize the applied magnetic field along the sample direction. Most ESR spectrometers has dual sample cavity. One is for sample and the other one is for standard material. An oscillating magnetic field is superimposed on the DC. It adds AC component in the diode current. With the modulation is of low frequency, around 400 cycles per second or less, the coils can be mounted outside the cavity and even on the magnet pole pieces. Modulation coil. The modulation of a signal at a frequency consistent with a good signal-noise ratio in the crystal detector is accomplished by a small alternating variation of the magnetic field. The variation is produced by supplying an AC signal to modulation coil oriented with respect to the sample in the same direction as the magnetic field. Crystal detector. The most commonly used detector is silicon crystal detector, which acts as microwave rectifier. The detector converts the absorbed microwave signal into a measurable electrical signal. The display devices. In order to observe the signal, a system is connected to with the computer. Isolators. It's device which minimizes vibrations in the frequency of microwave produced by a klystron oscillator. Isolators are used to prevent the reflection of microwave power back into the radiation source. It is a strip of ferrite material which allows microwaves in one direction only. It also stabilizes the frequency of the klystron. Couplers and matching screws. The various components of the microwave assembly to be coupled together, making use of the risers or slot of various sizes. So now let us concentrate on applications of ESR spectroscopy. It is used to study about the free radicals. One can study the free radicals by using ESR spectroscopy even in very low concentrations also. The structure of organic and inorganic free radicals can be identified. It is used to investigate the molecules in the triplet state. The spin label gives the information about the polarity of its environment. Structural determination. In certain cases, ESR provides the information about the shape of the radicals. It gives the reaction velocities and mechanisms. It is used to investigate the inorganic compounds. It is used to study the catalyst. It is used to determine the oxidation state of a metal. Analytic applications. It can determine Mn2 plus ions. It can determine the vanadium. It can determine the polynuclear hydrocarbons. Biological applications. The presence of free radicals can be found in healthy and diseased conditions. Functioning of most of the oxidative enzymes can be confirmed. Here are some more medical applications of ESR spectroscopy. It can detect the free radicals. ESR spectroscopy is a powerful way to detect free radicals that are generated in biological system or chemically. One can study the interactions. ESR spectroscopy can be used to study how biologically relevant system can interact with the metal ions, organic molecules, and nanomaterials. One can study the radical intermediates. ESR spectroscopy is used to study radical intermediates in organic reactions. For example, it is used to show that radicals are generated and decayed during oxidation caused by enzymes. ESR spectroscopy is a non-destructive analytical method that can provide structural information about paramagnetic spaces. It works out by exposing a sample to a strong magnetic field which causes the electronic energy levels of atoms or molecules to split. The absorption frequency of the microwave radiation that is absorbed by the unpaired electrons depending on the local environment. So there are a lot of applications on ESR. So right from biological, physiology, pharmacology, agriculture, food science, medicine, material science, physics, chemistry, and biochemistry. So there are a lot of applications in various fields. ESR spectra line shape gives insight to dynamic process, molecular motions, or fluidity. It can probe the structure of active sites in metalloproteins. It can measure the sterilization of medical goods and foods. It can detect the irradiated foods. The enzymes, catalyzed biological redox reactions can be studied. It is used to study the transition metal complexes. It is used to study the N-type semiconductors. And it is used to study the presence of organic and inorganic radicals.